Guys, welcome back. Fred here at Math and Engineering. I'm going to do a quick problem for you on the application of influence lines, namely the absolute maximum response. So in this question we have a beam, it's a plate girder, it looks like a bridge, it's about 50 feet long, and we have a truck passing over it, and it contains a series of concentrated loads in the form of wheels, and one of the wheels is 4 kip and the other 2 are 16. We're asked to determine the absolute maximum bending moment in the simply supported beam due to the wheel loads of the truck above. Perfect. So, first step in a question like this is to simply rewrite the loads over here on a nice fresh free body diagram, you can call it, if you'd like. Alright, and we have 14 feet here and 14 feet still. Okay. So, the first thing to do is to sum up these forces and get the resultant force, okay? So, PR, we'll call it PR, okay? And that's equal to 4 plus 16 plus 16, so that is 36 kip. Okay. Very good. Now, we need to see where the resultant force acts within the series of these 3 loads. Okay, so that's going to be important. We want to know the distance. And what we can do, so if we take a look at any point on here, and I'm just going to choose this point because we're going to be taking kind of like a moment here. So if we do it on a point, it's just less work for us. We can take 2 moments instead of 3 if I take it over here, for example. But the idea is that the sum of the external loads acting on this point, the moments of the external loads acting on this point, is equal to the resultant force times the distance to the resultant force. Okay, so what that looks like in equation form, okay, is we have the resultant force times x bar. Okay, so we'll say that PR, for example, is somewhere here, but it's an unknown distance. Okay, we'll call the unknown distance, and we're starting from here. This is our point of reference. We're going to call this x bar, okay, and it's some distance from here, but we're not sure. Okay, and that is equal to the sum of the external forces, okay, acting, not including this, times the distance to the point. So we have 16 times 14 plus 4 times 28. Okay, and if we plug in 36 here for PR and divide this whole side by 36, we get x bar is equal to 9.33 feet. Okay, so that means that x bar is equal to 9.33 feet. Very good. Okay, so we know that this distance is 9.33, and there we go. I'll just draw a line there. And there's a little formula here that might help you out. Okay, we have, and this distance here, okay, is called x. Okay, so x is the distance from the closest load to the resultant force. Okay, and x is simply x bar over 2. Okay, and that is 9.33 over 2, and we'll call that 4.67. Okay, so this distance here is 4.67 feet. Okay, very good. So we have a distance x here of 4.67 feet, all right? And there's a little something to note here, okay? So generally, a good thing to note here, and this is a trick, okay, is the one thing to know is that when we place the 3 loads on the beam, the maximum bending moment is going to happen under the second load of the series, so the 16 kip. What's also important to note is that if the closest load in the series of 3 is the largest load or equally large as the adjacent loads beside it, then that is where the maximum bending moment is going to occur. In this case, 16 and 16 are the same, and 16 is more than 4, so we know that since PR is closest to the center load, it's going to happen there. Okay, if it wasn't the case, if, for example, the right load was 17, okay, then we'd have to evaluate that one too. But in this case, we know that the maximum bending load is going to happen under the second load in the series, okay? Now we need to take a look, and this is our beam, okay, so this beam is this one here. So it's 50 feet, okay? And what we need to do is, and this is really simple, okay? So we have our center line here of our beam, okay? And what we do, okay, is you make a line, or you divide the distance, okay, between your resultant force and the largest closest force to it, okay, or the closest force to it, which is 16, okay? And that is going to be 4.67 divided by 2, okay? And we're just going to place these loads here with at a distance of x over 2 from PR and x over 2 from 16. Okay, so we have 16 kip here, okay, and we have PR here, which is 36. Okay, that's our PR. And these two are 4.67 divided by 2. Okay, so we have 2.33. Okay, and now we just place the loads in exactly the same spot as they were before, according to this, okay, because the loads, the spots haven't changed, but we've only placed them in the spot where they're going to create the maximum bending moment on the beam. So, this 16 kip force that is to the right of PR is 9.33 feet from it, right? And this is 9.33. And we have a 4 kip over here, okay, and that's 14 feet in distance. Cool. So now this is just a matter of kind of finding out distances and stuff like that. And now all we need to do, okay, is we need to calculate the vertical reaction. So we'll calculate it. We'll call this A and we'll call it B. Okay, we need one vertical reaction in order to solve this, because what we're going to do is we're going to cut the beam and we're going to solve for the maximum bending moment and the value of it. So let's solve for A here, okay? So if we solve for A by, for example, taking the moment about B and simply using, instead of these three forces, using the resultant force, okay, what we get, and if we take a look, okay, and we know that this distance is 9.33 and this distance is 2.33. Okay, so this distance from here to here, okay, and I don't want to write too much on here because it'll get messy, but this distance from the center line to the 16 kip foot is 11.66, and we know this whole distance is 25, so 25 minus 11.66, and this is 13.34, okay, so we have 13.34, and now what we can do is we can go ahead and calculate, since we have that distance now, let's take the moment about point B. Okay, so the moment about B, we're going to simply multiply PR, which is 36, okay, and that's going to be negative, times 13.34 plus 9.33, so we have 22.67, very good, and that is going to be plus AY times 50, right, because AY is over here, and we have 50, that's equal to 0, okay, and if we calculate that, AY is simply going to be 16.32 kip, okay, and the final step in this problem is to solve for the bending moment, okay, and where does the bending moment occur? The bending moment occurs under the second load in the series, okay, so the second load in the series, we're going to go here, all right, we're going to cut the beam right here, okay, so what that's going to look like is, this is A, okay, and we found A to be 16.32 kip, and we have a 4 kip load here. We can just go back and calculate this, so we have 14 feet here, we have 2.33, right, so we have 25 minus 14 minus 2.33, okay, that's 8.67 feet there, so we have 8.67 feet. So we have our AY, we have our 4K, and then we have, if we go over here and we're going to cut the beam, okay, this is under the second load, and to the second load is 14 feet, okay, and we have a moment here, okay, so therefore, okay, our moment is equal to, okay, and that's what direction is this, guys? Well, if we do counterclockwise, that's going to be negative, okay, so we'll put it the other side, okay, we're going to have M is equal to, okay, 16.32 times that entire distance, which is 14 plus 8.67, 22.67, okay, minus 4 times 14. And that is simply equal to 313.97 kip feet. Okay, so the maximum bending moment, absolute maximum bending moment, which occurs under the second load, so this load here, okay, is equal to 313.97 kip feet. I drew up that so you can see it a little bit better. And that's pretty much it. So, that made sense to you? I know it's a little bit messy. It gets a little messy around here, so I had a little bit of trouble kind of showing you exactly what was going on, so I hope I didn't confuse you there. Thanks for watching, much appreciated, and like and subscribe.